Welcome to the Introduction to Battery Technology course. This lecture focuses on Chapter 2, which covers the operational factors of battery systems. We will discuss conceptual battery performance and trends without referencing any specific battery, experiment, or manufacturer. Our goal is to establish a comprehensive understanding of how batteries function under real-world conditions and the factors that influence their performance. By the end of this section, you should be able to explain the fundamental electrochemical properties that define how a battery behaves when charging, discharging, and aging over time. Remember, a battery is not just a static energy storage device. It is dynamic, and its performance is shaped by many variables, both internal and external. Learning objectives. The objectives for this chapter are straightforward. First, we aim to provide you with a comprehensive overview of battery performance characteristics, so you understand how a cell's behavior can vary depending on usage conditions. Second, we aim to establish a foundation for understanding the electrochemical properties that are involved during battery operation. To put it simply, this chapter is about bridging the theory of how batteries work with the reality of how they perform in the field. Some of the key factors we will explore include state of charge, temperature, battery age, and other influences that directly affect battery voltage, energy output, and long-term durability. Key terminology. Before we dive in, let's review some essential terms. Factors refer to circumstances or influences that shape a result. In our case, how a battery performs. A cycle refers to one full charge and discharge sequence of the battery. The number of cycles a battery can complete before losing capacity is a critical performance measure. Voltage is the potential difference expressed in volts, while current is the flow of electric charge measured in amperes. Resistance measures how much a material or device opposes the flow of current. According to Ohm's law, resistance equals voltage divided by current. We also need to understand terms like cycle life, which refers to the number of cycles a cell can sustain before its capacity drops below 80% of its original value, and discharge, which is the process of releasing stored energy. These are the key terminologies you will learn throughout the chapter. When analyzing battery operation, it is essential to understand certain operational parameters. Cell voltage, the basic electrical potential a cell provides. Capacity, measured in ampere hours, indicates how much charge the cell can store. Energy, expressed in watt-hours, is essentially capacity multiplied by voltage. Energy density and specific energy, which measure how much energy can be stored relative to volume and mass, respectively. Other critical parameters include state of charge, SOC, which indicates the battery's level of charge, depth of discharge, DOD, which measures the percentage of the battery's capacity used, and internal resistance, the opposition within a battery to the flow of current, which causes energy loss as heat and affects voltage output during charging and discharging. Understanding these parameters enables us to evaluate battery design, performance, and suitability for various applications. One of the key performance parameters is the state of health, also known as SO. This compares a battery's current performance with its performance when brand new. Engineers examine several key factors: voltage stability, internal resistance, the rate of self-discharge, and the battery's ability to accept a charge. A battery is generally considered at its end of life when its full charge capacity falls below 80% of the initial rating. This definition is important because it sets the threshold for when a battery is no longer considered reliable for its intended use, even if it still works. When we talk about battery voltage, we need to understand two important limits: the maximum voltage during charging and the minimum voltage during discharging. As a battery charges, its voltage gradually increases. But there is a voltage limitation, which is the maximum safe level the battery can handle. If we go above this limit, the battery can overheat, become unstable, and in extreme cases, even create hazardous conditions. Overcharging is one of the main reasons batteries fail or become dangerous. On the other side, as the battery discharges, its voltage decreases. Here, we have what's called the cutoff voltage. This is the lowest point at which the battery should be allowed to discharge. If the voltage drops below this level, the internal chemical structure, the so-called active mass, can become unstable. That instability shortens the battery's life and reduces its capacity. For lithium-ion batteries specifically, The cutoff voltage is typically between 2.7 volts and 3.0 volts. Discharging below this level risks permanent damage. The illustration on the slide represents this idea. As the battery moves from fully charged to empty, the voltage gradually decreases. However, it must never exceed the safe upper and lower limits. In short, maintaining proper voltage boundaries is essential to keeping a battery safe, stable, and long-lasting. Let's talk about why lithium-ion batteries are so special compared to older battery technologies. One of the biggest differences is the operating voltage. A single lithium-ion cell typically delivers approximately 4 volts, while a nickel-based cell, such as nickel-cadmium or nickel-metal hydride, provides only about 1.2 volts. This higher voltage comes from the chemistry of lithium itself. Lithium is the most electronegative, electron-donating metal, meaning it strongly attracts electrons. When paired with an organic electrolyte instead of a water-based electrolyte, it enables significantly higher voltages. If we tried to use a water-based electrolyte, the voltage would be so high that water would break down through electrolysis instead of allowing the battery to function. So why does this matter? With higher voltage, we can design batteries that are smaller and lighter, but still deliver the same or even more power. This is one of the key reasons lithium-ion batteries became the foundation of modern portable electronics and electric vehicles. They provide more energy in a smaller, lighter package. One of the big advantages of lithium batteries is that they can store the same amount of energy as other battery types, but in a much smaller and lighter package. This ability to shrink in size while maintaining performance is called miniaturization. And it's one of the reasons we've seen such rapid growth in portable electronics and cordless devices, from smartphones and laptops to power tools. Simply put, without lithium batteries, many of the compact products we rely on today would not have been possible. Check the slide for the quote from the U.S. Environmental Protection Agency. Battery performance by discharge. This graph illustrates the variation in discharge voltage of different battery types as they are used. On the horizontal axis, we have the percentage of capacity discharged, also called depth of discharge or DOD. On the vertical axis, we see the battery voltage. For all chemistries, the trend is similar. As the battery discharges, the voltage gradually decreases. Notice that the decrease is fairly steady until the battery is close to about 90% discharge. At that point, the voltage drops very quickly, approaching what we call the cutoff voltage. This is the minimum safe voltage for the battery. Going below it can damage the internal materials and reduce the cell's lifespan. What's also important here is the difference between chemistries. Lithium-ion batteries start much higher, around 4 volts, compared to nickel-based batteries, which are closer to 1.2 volts, or lead-acid at around 2 volts. This higher voltage is one of the reasons lithium-ion packs store so much energy in a smaller size. The key takeaway is this. No matter the chemistry, batteries don't deliver a perfectly constant voltage. They gradually decline as they discharge, and then experience a sharp drop near the end. That's why devices need battery management systems to cut off power before the voltage falls too low. Battery performance measured by specific energy. Specific energy indicates the amount of energy a battery can provide per unit of its weight. It's calculated by multiplying capacity by voltage, then dividing by mass, and it's especially important in applications like electric cars, where saving space and weight is crucial. But in real-world use, the actual specific energy is much lower than the theoretical maximum. This is due to inefficiencies within the battery. Reactions do not utilize all active materials, internal resistance produces heat, and ion movement within the electrodes is not optimal. Because of these losses, the energy we can actually use is only about 25 to 35% of what's theoretically possible. This gap explains why battery research focuses on improving materials and design to push performance closer to that ideal. Refer to the graph and equation presented on the slide. Battery limiting factors. When discussing battery performance, it's equally important to understand what limits it. First, the surface area of the electrodes. A larger area allows more reactions to occur and improves output. Second, the catalytic activity of the electrodes. For example, lithium intercalating into graphite at the anode directly impacts the rate at which reactions can occur. Third, we have electrolyte conductivity. If the electrolyte doesn't allow ions to move efficiently, internal resistance increases and performance drops. Finally, the nature of the reactions on electrodes can be a problem. Sometimes, unwanted side reactions occur, such as the formation of metallic deposits inside a lithium-ion cell. These don't produce power, but can cause damage and reduce the overall life of the battery. Together, these factors define the limits of how efficiently and safely a battery can operate. Modes of discharge. In batteries, there are 3 common modes of discharge: constant current, constant resistance, and constant power. To understand how these modes behave, we begin with Ohm's law, which states that voltage equals current times resistance. From this, we can also calculate power in different ways. Power equals voltage times current, or current squared times resistance, or voltage squared divided by resistance. By applying Ohm's law together with these power equations, we can predict the shapes of current and voltage curves during each mode of discharge. This provides the foundation for comparing and analyzing how a battery responds under various operating conditions. Continuing with the modes of discharge, 2/3 on this slide, we examine how current changes over time under different discharge modes. The solid horizontal line represents constant current discharge. Here, the current remains steady throughout the process, even though the battery voltage gradually decreases. For constant power, the situation is different. Since voltage naturally drops as the battery discharges, the current must increase to maintain constant power output. That's why the curve slopes upward. And finally, with constant resistance, which is the most common case, both voltage and current decrease together over time. This happens because as the voltage drops, the current through a fixed resistance also drops. So, the key takeaway is that the mode of discharge has a big impact on how the current behaves during battery operation. Mode of discharge. 3/3 this graph illustrates the variation in voltage over discharge time under different operating modes. Notice that when operating at constant power, the voltage drops off the earliest. That's because to maintain steady power, the current must increase as voltage naturally decreases, which pushes the battery harder and leads to earlier voltage collapse. Constant current performs slightly better, but still exhibits an earlier cutoff compared to constant resistance. With constant resistance, which is the most common mode in real devices, both voltage and current decline gradually. Therefore, the voltage drop-off occurs last. This comparison helps us understand how different discharge conditions affect usable capacity and battery performance. Discharge current effect on voltage. When discussing how discharge current affects battery voltage, we often refer to the concept of C rate. The C rate represents the current required to fully discharge a battery in 1 hour. For example, if a battery has a capacity of 100 amp hours, then 1 C equals 100 amps. Now, as the discharge current increases, more electrons are being transferred from the anode to the cathode. According to Ohm's law, if the load is constant, this increased current causes a larger voltage drop. Essentially, the higher the current, the lower the voltage during discharge. Additionally, as the current increases, the battery's useful capacity decreases. This means the battery reaches its cutoff voltage much faster, even though its theoretical energy storage hasn't changed. On the graph, you can see how higher currents, labeled I1, I2, and I3, result in progressively steeper voltage declines and shorter overall discharge times. Let's discuss one of the important phenomena in battery technology: self-discharge. Self-discharge refers to the gradual loss of battery capacity over time, even when the battery is not connected to any device or load. This occurs due to internal chemical reactions that naturally take place within the battery, consuming stored energy without any external use. This means that even if you store a fully charged battery on a shelf, it will not remain fully charged indefinitely. Over time, its voltage and capacity will decrease, which can impact performance, particularly in applications where long-term storage is crucial. Different battery chemistries have different self-discharge rates. For example, nickel-cadmium, NaCd, and nickel-metal hydride, NMH, batteries tend to lose charge relatively quickly. In contrast, lithium-ion batteries have the lowest self-discharge rate, making them ideal for devices that sit idle for extended periods, such as smartphones, laptops, and backup power systems. So, when choosing a battery for your application, especially one that involves long-term storage or infrequent use, consider the self-discharge rate. Lithium-ion batteries are often the best choice when you need reliable energy retention over time. Temperature trends and their effects on battery performance. As temperature increases, several significant changes occur in battery behavior. First, the electrochemical reaction rates speed up, which improves performance in the short term. Internal resistance also drops, allowing current to flow more easily, which results in higher voltage and increased capacity. However, these benefits come with trade-offs. Higher temperatures also lead to faster self-discharge, meaning the battery loses energy even when not in use. More critically, elevated temperatures accelerate aging and material degradation, which shortens the battery's overall lifespan. Examining the graph, we can observe how specific energy changes with temperature across various battery chemistries. Lithium-ion batteries stand out. They exhibit stable and even improved performance as temperatures rise, making them a reliable choice in environments with fluctuating or elevated temperatures. Temperature trends, voltage versus capacity. This slide examines how temperature affects battery capacity when the current is held constant. As the temperature increases, the battery can deliver more capacity before reaching the point where the voltage begins to drop. This means higher temperatures allow the battery to operate longer before hitting its cutoff voltage. The graph illustrates voltage as a function of capacity across 4 temperature levels, labeled T1 through T4. T1 is the lowest temperature, and T4 is the highest. T3, which represents 25 degrees Celsius, is considered the nominal operating temperature. At this temperature, the battery typically achieves 100% of its rated capacity. As we move from T1 to T4, you'll notice that the voltage curves extend further along the capacity axis. This indicates that the battery performs better at higher temperatures in terms of capacity. However, it's important to remember that while performance improves, higher temperatures can also accelerate aging and reduce long-term reliability. In this final slide on temperature trends, we're focusing on how heat affects long-term battery degradation. The graph shows the percentage of capacity loss per year across 4 different battery chemistries as temperature increases from 0 degrees Celsius to 50 degrees Celsius. On the y-axis, we see the degradation rate, and on the x-axis, the temperature range. What's clear from the graph is that all battery types degrade more quickly at higher temperatures. The trend is linear, meaning the hotter it gets, the faster the battery loses capacity. Among the chemistries shown, Li-ion batteries experience the highest rate of capacity loss at elevated temperatures, while NCD batteries show the lowest degradation under the same conditions. This reinforces a key takeaway. Higher temperatures accelerate self-discharge and long-term degradation, thereby shortening the battery's lifespan. That's why thermal management is so important. Keeping batteries cool helps preserve their health and performance over time. In this slide, we explore 2 key measures of battery longevity. In this slide, we examine the bathtub curve, a classic model used to describe failure rates over the lifespan of a battery or any other electronic component. The curve has 3 distinct phases. Early failures, also known as the infant mortality phase. This typically occurs at the beginning of a battery's life, when failures are often due to manufacturing defects or material inconsistencies. The failure rate starts high but drops quickly as these weak units are identified and removed. Stable operation, or the useful life phase. This is the longest and most reliable period in a battery's life. Here, the failure rate is low and relatively constant. The battery performs consistently, with degradation occurring slowly and predictably. Wear-out failures, which happen toward the end of the battery's life. After many charge-discharge cycles, the battery begins to degrade more rapidly. This is due to aging, electrode wear, and chemical breakdown. The failure rate rises again as the battery approaches the end of its usable life. Understanding this curve enables us to plan for effective maintenance, replacement, and design strategies. It also highlights the importance of quality control early on and effective battery management throughout the battery's life to delay the wear-out phase. This graph illustrates how cycle life decreases as the depth of discharge increases. In other words, the deeper the battery is discharged before recharging, the fewer cycles it can complete over its lifetime. You'll also notice that higher temperatures further reduce cycle life. Therefore, both temperature and depth of discharge are crucial factors in determining battery longevity. To extend cycle life, it's best to use shallow cycling, charging before the battery is fully discharged, and to operate at lower temperatures whenever possible. The battery selection table shown in this slide provides a general overview of common battery types and their performance parameters. While lithium-ion batteries perform exceptionally well in some areas, depending on the specific application, other systems may be preferred. For example, for larger batteries, the cheaper cost of other batteries might be preferred. This marks the conclusion of Chapter 2 of the Introduction to Battery Technology course. For deeper insights, please refer to the references provided on this page and consult the textbook to further solidify your understanding of the concepts introduced in this chapter. Once you feel confident with the material, you are encouraged to explore the additional resources available in this module, including recommended YouTube videos and supplementary readings. These will help you reinforce your knowledge before moving on to the practice exercises and, ultimately, the end of module assessment. Thank you. We'll meet again in the next lecture. Thank you. We'll meet again in the next lecture.